All right there. Hi guys, my name is Wilfrid and I'm a senior math tutor. So I'll be bringing you guys through 10 questions surrounding calculus and integrals and derivatives. A little bit of a backstory upon myself. I graduated from a master with a major in biochemistry and a minor in mathematics. And the questions that I'll be covering today will be from OneClass. So if you have any other questions, please submit them through OneClass. So let's begin. Okay, so the first question is, what is the antiderivative of x divided by x plus 1? So another word for antiderivative is integral. So they're asking us to solve the integral of x divided by x plus 1 in terms of dx, okay? So the junior tutor stated the formulas that will be used, okay? So they stated that they'll be using the constant multiple rule of differentiation, which states that a constant multiple in front of a variable will be derived like so. The difference rule, so the integral of a function subtracted by a function can be split up into two different integrals. The constant rule of integration would suggest that a constant that's integrated will produce a variable plus another constant, and the logarithmic rule of integration, which states that integral of 1 over x is equal to ln of x plus a constant. So the technique that we'll also be using is a substitution technique. And by doing so, we simplify the integral in a way that we can solve it easily, okay? All right, so let's begin. So we have the integral of x divided by x plus 1. Okay, so we're going to use a substitution. So we're going to call variable u, and we're going to call variable u to be equal to x plus 1, okay? That means that x equals u minus 1. Okay, so let's just label this 1 and this 2. All right, and finally, if we took the derivative of du in terms of x, we will get du of dx. Du of du equals to 1 dx. Okay. I just simply derived it and I moved the dx to the other side to get this. Okay. So we're going to use this substitution to change our integral. Okay. But so by using 1, 2, and I'll also name this 3. And 3, we can change our integral to equal the integral of u minus 1 divided by u of du. Okay, so now we're integrating in terms of the variable u. So in this integral, we can break it up and we can simplify this fraction to be integral of 1 minus 1 over u du. We use the difference rule of integration to separate this integral into the integral of 1 du minus the integral of 1 over u du. Okay, and we know that using the constant rule of integration that this just equals to u, and this just equals to ln, so minus ln of u. We can't forget our constant here, and we're just going to sub back u in, so sub u equals x plus 1, and we get x plus 1 minus ln of x plus 1 plus c. So that's our indefinite integral of x over x plus 1. Okay. So the junior tutor also did the same solution, and this is a very organized one. They stated what kind of principles that they'll be using, and they went through step by step on how to use those principles and apply them. And they came up with the answer to our indefinite integral. So this solution is detailed and correct. Nice. Cool. All right, let's move on to the second question. All right, so the second question reads, how do you integrate y equals x times e to the power of negative x? So last time we used a technique of substitution, and this time we're going to be using a technique called integration by parts. It's also a technique that simplifies your integral so that you'll be able to solve it more easily. So let's write down our integral first here. So we're integrating in terms of x here, so we're going to write the integral sign of x e to the power of negative x d of x, okay? So the integration by parts formula suggests that we take two separate substitution variables, and those two variables can be expressed as the integral in this way. So the integral of, let's say, u and in the terms of d in terms of v is equal to u times v minus the integral of v in terms of u. Okay, so we're going to take our substitution variables and we're going to somehow manipulate our x and e to the power of negative x to have two separate substitution variables here. Okay, so let's set u to be equal to x. That means d of u, or du in terms of dx, is equal to 1 of dx. Okay, and we're going to take our dv to be equal to e negative x in terms of x. Okay, and if we were to integrate this, we would get v equals negative e negative x. Okay, plus a constant c, which doesn't really matter. Okay, so now we're going to rewrite our original integral into the integration by parts. So this equals to u times v, so x times negative e over x. So x times negative e to the power of negative x minus the integral of v du, which is just integral of negative e negative x to the power in terms of x, because our du is just dx, right? So this is now our integration by parts by using the substitution, okay? So now you see here that we simplified the integral that we're supposed to calculate, right? Because it only has one term here, and we don't need to deal with this pesky x variable, right? So if we were to solve this would be x times negative e negative x minus, it would be e negative x. Okay. Minus, so this be minus. No, just think this. Yeah. So that's how we solve that. Okay. And we need to add a plus c, of course. And now, therefore, the integral of x times e to the negative x dx equals x negative x times e to the negative x minus e to the negative x. Okay, cool. So that's the answer to our question here. And the junior tutor also came to the same solution. They used integration by parts. They stated the formula for integration by parts, and then they found their substitution variables, and they solved integral by using integration by parts, and they came to the solution here, which is negative x times e to the negative x minus e to the negative x plus c. The only difference in our solution is that they factor out negative e to the negative x. So maybe I should write out that solution actually, just to be consistent with this. So this equals x plus 1 plus c. Okay, cool. Cool. All right, moving on to question number 3. All right, question number 3. Find the maximum rate of change of f of xy at the given point and the direction in which it occurs. Okay, so this is a multivariable question, and it's asking us to find the slope at a given point at these functions, I guess you can say, and at these given points. So it's asking us for the maximum rate of change and a known fact. So let me first define what we're trying to solve for here. So we are looking for the gradient of f of xy, okay? And the gradient of f of xy can be described as a vector valued function of the partial derivatives of f of xy. Okay, so the partial derivative of this and the partial derivative of this. So this is for a two-variable function, but in general, right? If we were to write out the general formula for it, let's say there's x, y, z, dot, dot, dot. It would be the vector value function of all the partial derivatives of the function. Okay, so we can keep going here. All right, so that's the gradient. Okay, so what they're asking for is us to find the gradient, plug in the points, and it is a known fact that the maximum rate of change occurs when at the magnitude of the gradient, right? So the magnitude of the gradient can be seen as this equation here. Okay, sorry that it's a little bit small, but it's basically the square root of the partial derivatives at x of y for each partial derivative squared, and that's your magnitude. Okay, so the maximum rate of change at f of xy at a given point will be the magnitude of that gradient at that given point. Okay, so the question here gives us two functions, so I'll be working through both of them today. So let's work through the first one first. Okay. All right. So 1. So our function is f of xy equals 4y times root x at the given point 4 and 9. Okay. So first of all, we're going to need to find our gradients, right? So the gradient of f of xy is the partial derivative at x and the partial derivative of xy at y. Okay. So if we were to look at our function here, so the partial derivative of x of our function would be 2y x to the power of negative 2. Let me just check to make sure that's correct here. Yep, so 2y to the power times x to the power of negative 1 over half. And our partial derivative of y would be 4 times root x. Okay, so these are our partial derivatives. All right. So now we're going to calculate the gradient at a given point 4, 9. Okay, so the gradient at 4, 9, what would that be? That would be 2 times 9, that's 18, times divided by 4, which is rooted, so that's 9. Okay, and the y value would be 8, because it's 4 times root of 4. Root of 4 is 2, so 4 times 2 is 8. Okay, so this is our gradient at 4, 9, 9 and 8. Okay, so now we need to find the maximum rate of change, and we know the maximum rate of change is just the magnitude of the gradient of 4, 9. Okay, so the gradient of f of 4, 9 is the square root of 9 squared plus 8 squared. Okay, and that equals to 81 plus 64, which is 145. Root 145. And finally, it's asking us for the direction. Okay, so the direction of our maximum rate of change will occur in the very direction that we calculated, in the very direction of the gradient itself. Okay, so in this case, all we need to really do is calculate the unit vector of the gradient of 4, 9 and divide it by its magnitude to find its direction. Okay, so its direction would be the unit vector, so let's say u, which equals to the gradient of f at 4, 9 divided by the magnitude of f at 4, 9. Okay, and that equals to 9 divided by root 145 and 8 divided by root 145, which in the end, that just equals 9 times root 145 over 145, and 8 times 145 divided by 145. Okay, so this is the unit vector, and this is the direction of our maximum rate of change. Okay, cool. So let's move on to problem number 2. Hopefully I can do it over here. All right, let's try to do it over here. Okay, so our function here is, so this is a 3-variable function, x, y, and z, and it's root of x squared plus y squared plus z squared at 9, 7, and -2. Okay. All right. So first of all, you need to calculate our gradient. All right. So gradient of f(x, y, z) is the partial derivatives of x, y, and z in that order. Okay. So the partial derivative of x would be 2x divided by x squared plus y squared plus z squared -half. Maybe I can scroll a little bit more over here. Okay. Our partial derivative of y would be 2y. So this is chain rule, right? So we're going to do the outside function, which is just half. Oh wait, this should be a x actually. Hold on, sorry. You know, I'll just do it for you guys here. So we're doing a chain rule, right? So it's the outside function, which is the square root first, and then it's the inside function, which is just x squared. Everything else is constant in a partial derivative, okay? So there should be a y over x squared plus y squared plus z squared -half. And we have z of, sorry for my really tiny writing, y squared plus z squared half. Okay, so this is our partial derivative of this function. Okay, so now we're going to plug in 9, 7, and -2. Okay, so bear with me, guys. So 9, 7, and -2. So the first one's going to be 9 divided by 81 plus 49 plus 4, which is 81 plus 49. That's 130, 134. The square root of 134. All right, 7 over the square root of 134, and -2 divided by the square root of 134. Okay, so this is the gradient at this x, y, and z. All right, and now we're going to need to calculate the magnitude. Okay, so the magnitude of this equals square root of 9 divided by, 9 divided by the square root of 134 plus 7 divided by the square root of 134 squared 2 plus -2 divided by 134 square root squared. Okay, so this would equal to, let me make my bracket bigger, 81 divided by 134 plus 49 divided by 134 plus 4 divided by 134. Cool. We're going to add these fractions up. 81 plus 49 is 130, plus 4 is 134. So all we get in the end is square root of 1, which equals Okay, cool. So we calculated the gradient. Okay, and now all we need to do is calculate a unit vector, which is just this. So let me say unit vector v. Whoops. So unit vector v would be the gradient of 9, 7, and -2 divided by the magnitude of the gradient of 9, 7, and -2. Okay, so that would equal this divided by 1, which would just equal this. Okay, cool. So the junior tutor solution is almost there, I would say. Actually, I think they got it right. That point equals 2, and they divided by 2. Okay, so incidentally, they got it right, but when they were doing the partial derivatives, they forgot to factor in a 1/2, because when you're doing your chain rule for this, right, you need to be conscious about the fact that you're taking a 1/2 and then minus 1. So the exponent here would be -1.5, but you also have to make sure that you take out the exponent before. And they didn't do that, so they actually added an extra 2 here. But in the end, they still got the right answer. So the solution to part 1 is correct. However, the solution to part 2 is almost technically is almost correct. Excuse me. When you forgot to account for the factor 1/2 when you partially derived f of x, y, and z. Okay, so unfortunately this solution there's a little hiccup here, so the solution is actually incorrect. Okay, cool. Let's move on to question number 4. I'm sorry for the small writing. I'll try to figure out how to expand the board as I continue to do these longer questions. All right, so the next question is find the local maximum and minimum values and saddle points of the function, and they provide us with 2 functions again. Okay, so we need to classify what a local extremum is, first of all, okay? So a local extremum is somewhat like a critical value, but it's for mostly multivariable functions. So a local extremum occurs when the partial derivatives of f of function f. So this could be 2 variables, 3 variables, 4 variables, are all 0. So when the partial derivatives of function f are all 0, that means that at that point there is no rate of change at any direction. X, Y, Z, W, U, V, how many variables you have, okay? And so not only do we need to know what a local extremum is, the question is asking us to find the local maximum, minimum values, and saddle points of the function. So we also need to go a step above calculating the local extremums, and we need to classify these points. So the second derivative test helps us do that. So we use what we call a discriminant, and the junior tutor writes it out here. So the discriminant is just a way of testing whether or not, or to classify your local extremum. So the discriminant is given by the double partial derivative of f times the double partial derivative of y minus the mixed partial derivative of f, so xy. And so this calculates us, this helps us classify the local extremum. So if the discriminant is positive and the double partial derivative of the partial double derivative of x of the function is greater than 0, it has a local maximum. If it's less than 0, it has a local minimum. Conversely, if the discriminant is less than 0 or is negative, that means it has a saddle point. Okay, so let me kind of show you what a saddle point looks like. All right, so you guys all are aware of like your local maximum, I guess. So it's like a, your vertices are like here, right? Let me use a different color. So this is like a local maximum, right? I guess like this is like a local minimum, right? That's a local minimum. Sorry, that's not black. That's like a local minimum. So a saddle point is neither a local maximum or a local minimum, and it looks like this. So there's a point. There's a point of inflection here, but there's not a local maximum or local minimum, and we call these a saddle point, right? So the rate of change at this point is still 0 at all partial derivatives, but is not a local maximum or a local minimum, and we use the discriminant to help us find that. Okay, so we calculate the double partial derivatives and use the discriminant to classify local extreme. Okay, sure. So now we're going to try to solve both of these functions together. So the first step is to, first of all, calculate its partial derivatives. Okay, so our first function here is f of xy. Maybe I can make this thicker. Let's make it like this. Okay. So f of xy equals x squared plus xy plus y squared plus y. And I'll just do a boundary here. Okay. Cool. All right. So let's calculate our partial derivative first. So let's calculate f of x. All right. So f of x is just 2x. So what we're doing by partial derivatives means that we're only deriving in terms of x, okay? So any y's in there we treat as constants. So 2x plus y plus 0 because these have no x's in them, right? All right, sure. So f of y would be 0, x plus 2y plus 1, okay? Sure. So now we need to calculate when these equal to 0, okay? So let's set these to 0. And so this equals to 0 when y equals negative 2x. And this equals to 0 when x equals negative 2y minus 1. Okay, so we're going to sub these into each other. So we're going to sub this x into here to solve for the points where both partial derivatives are 0, okay? So sub, I'm just going to label these 2 and 1. So sub 2 and 1. And we get y equals negative 2 times negative 2 minus 1. And that equals to 4y plus 2. Okay, we still have a y here. So this equals to y equals negative 2 over 3. Okay, so now we're going to sub this y value back into our x value, which is, I guess, over here. So sub, let's label this to 3. Sub 3 into 2. And we get x equals negative 4 over 3 minus 1. Why is my x different? Huh. This should be 1 over 3. So we take our x, we sub that in, negative 4y plus 2. And then we moved it over, negative 3y, and then we divided it. Okay, and then we take 2 over 3. Oh, this should be a positive. Sorry, I found my mistake. Yeah, it's very Sorry guys about that. It's very easy to find mistakes when you're not paying attention. Okay. So what I did there is I added a negative when you're not supposed to add a negative, because negative cancel out here. Okay, so 4 over 3 minus 1, which equal to 1 over 3. Cool. We found our points. All right. Delicious. Okay, so now that we have found our points at which both partial derivatives are equal to 0, we're now going to calculate the double partial derivatives of both, okay? So the double partial derivative is equal to 2x, or just 2. The double partial derivative of y would equal 2. And we're going to do a mixed derivative, so a mixed partial derivative. So we're going to take our f of x and we're going to derive it in terms of y. And we get 1. Cool. All right. So now that we have done that, so we have found our local extremum, which is 1 over 3 and negative 2 over 3. But we need to classify it now, right? So we need to use our discriminant. So our discriminant is, to refresh, it's this, the partial double derivative of x times the double partial derivative of y minus the mixed partial derivative squared, I think. Okay, so this equals to 2 times 2 minus 1, which equals to 3. Okay, so what does this mean now? Okay, so going back to what the junior tutor wrote. So our discriminant is greater than 0, it's positive. And our double partial derivative of x, in fact, all the double partial derivatives are positive. So we have classified that our point 1 over 3 and negative 2 over 3 is a local maximum. Okay, so let's write our concluding statement. Since d is greater than 0 and our partial derivative is greater than 0, the point 1 over 3, negative 2 over 3 is a local maximum. Okay. All right. Cool. So that is the first function. Okay. So let's move on to our second function. So this time I'm going to do it a little bit quicker as I went through step by step on the last time. So as f of xy equals x minus y times 1 minus x times y. Okay, so we're going to expand this first. So f of xy equals x minus x squared y minus y minus xy squared. Okay, cool. We're going to take the partial derivatives. So you notice here that I'm using a different notation. This is equivalent to partial over partial x, partial f over partial x. I just write f of x to signify that I'm taking the partial derivative of x in terms of x. So the partial derivative in terms of x is 1 minus 2xy minus y squared, which would be a plus. Okay. Our partial derivative in terms of y is going to be negative x squared minus 1 plus 2xy. Okay, we're going to set these to equal 0. And what do we get? Okay, so we're just going to equal these two to each other because they both equal 0. Okay, so sub 2 and 1. And we get this huge equation. So 1 minus 2xy plus y squared minus x squared minus 1 plus 2xy equals to 0. We're going to simplify here. So this and this and this and this cancel out. So all we get is y squared minus x squared equals to 0. Okay. So now we have figured out that x equals to, if we move both sides cancel out, positive negative y, because we're square rooting a square, right? All right, so since x equals positive negative y, we're going to sub in when x equals y into our partial derivatives here. Okay, so let's label this to be 3. Also, let me scroll down a bit here. So sub 3 into 1, I guess. Okay. So when we sub 3 into 1, we get this equation. So let's sub positive y. Okay, so 1 minus 2 y times y, so y squared plus y squared equals to 0. Okay, move this one to the other side. This equals to negative y squared, but it cancels out because this 1 is moved over. So this equals y squared equals to 1, and that equals y equals positive or negative 1. So we found our local extremum. So local extremum, since there's multiple, I'm just going to write it out in a therefore statement. It's going to be 1, 1, and negative 1, negative 1. Okay, cool. All right. Around that, also let me zoom out a bit. Okay, sure. So I'm going to do the rest of the work over here. It's kind of crowded down there. Okay, so now we're going to calculate the second partial derivatives. So f of x equals to 2y, and f of y is going to be equal to 2x. F of xy is equal to 2x plus 2y. Okay, sure. Oh, there should be a negative. Okay, so now we're going to take our discriminant. So our discriminant is equal to, it should be negative 2. No, that should be positive. Okay, this should be negative. Negative 2x. Yeah. Okay, it should be negative 2y times 2x minus negative 2x plus 2y squared. Okay, so that equals to negative 4xy minus, let's expand this out, 4x squared minus 4xy, and this should equal to plus 4y squared. Yes. Okay. Cool. So we're going to plug in our values now, our saddle points here. Let me simplify this too. So negative 4x squared plus, so this is just plus minus 4y squared, because this and this cancel out here. Let me make sure I just did my expansion right here. I don't want to make any mistakes here. So 4x squared minus 4 should be 8 minus 4 negative xy plus 4y squared. Should just be 8. Okay. So negative 8xy. So this should actually be plus 4xy. Okay, cool. There we go. So that's our discriminant. So we're going to take the discriminant at 1 of 1. And that is equal to negative 4. Negative 4 plus 4, which equals negative 4. And we're going to take our discriminant of negative 1, and that equals 4 minus 4 plus 4, which is negative 4. Okay. And finally, we're just going to take f of x at 1, 1. which is just -2, and f of xx at -1, -1, which is just 2. Okay, this doesn't really matter, but therefore, since d of 1, 1 and d of -1, 1 is less than 0, we have that the local extremum 1, 1 and -1, 1 are saddle points. So we're going to refer back up to what our junior tutor wrote. So when a discriminant is less than 0, it has a saddle point. Okay. So we noticed here that both discriminants of our local extremum yielded us negative values. So now we know that they're both saddle points, and we have solved the question. So this was a very long question, and the junior tutor got it correct. So this solution is correct. Good work. Okay, cool. All right, let's move on to question number 5. All right, so how do you find dy of dx by implicit differentiation? Well, differentiation, wrong, differentiate. Given this function, okay? So implicit differentiation is a different way of differentiating functions when you have a function that is not easily explicitly differentiated. That means that the y is on one side and the x is on the other side, okay? So you see here that it's very hard to isolate for y, so we're going to use implicit differentiation instead, okay? So you take everything, all the terms, and you differentiate in terms of dx. And so I'll show you guys how to do that. So let's, first of all, let's write down, let me change my thickness again. Okay. So let's say d of dx of x times y cubed equals d of dx of y plus x. Okay. So we're going to use we have to be wary that there's a product rule here. So let's do the product rule first. Okay. So product rule is, so the derivative of x is just 1. So 1 times, so it'll be, let me just write it out entirely. So it'll be d of the x of y3, which is just 1. So x, derivative of x is 1. And then derivative of y cubed, so this is also a chain rule, right, times x. So derivative of chain rule would be plus 3y squared times x. And then we have to derive the inside, but we're going to just say y dy over dx for now, okay? So that's the left side, okay? So this was a product rule with a chain rule too, okay? So for the first one, we derived x, which is 1, and we left the other function alone, which is y cubed. And then we derived y cubed, which is also a chain rule, so we moved the 3 down, minus 1 on the exponent. And then we had to say dy dx because we have to just write that out because we don't really know what y is equal to, okay? So for the other one, this is just dy over dx plus 1, okay? So it's the derivative of y, which is just dy over dx, and then it will be just derivative of x, which is just 1, okay? So now we're going to isolate for dy dx, so we're going to move dy dx to the left side and everything else to the right side, okay? So we have 3y squared x dy dx minus dy dx. And then on this side, we have 1 minus y cubed, okay? So now we're going to factor out dy dx, which just leaves it with 3y squared x minus 1 equals 1 minus y cubed. And finally, we're going to move this whole term to the other side. So dy over dx equals 1 minus y cubed divided by 3y squared x minus 1. Okay, so we have now found implicitly differentiated for y in terms of x by doing through this method of implicit differentiation. Okay, So the junior tutor also did that, and they got the correct answer. So just to clarify a bit, so implicit differentiation, we don't know what y is equal to. So instead, we're just solving straight up for dy dx instead of isolating for y and then differentiating. That's why when we come down to the chain rule here, and when we come down to differentiating y, we just write dy over dx because that's what we're differentiating for. And then once we do that, once we have this step finished here, we're just able to isolate for dy over dx. And we notice that our derivative in the end is a function of both variables, okay? In explicit differentiation, when you derive, it'll be a function of your independent variable. But here we have dependent and independent here because we're unable to isolate for y, okay? All right, so the next question is, what is the derivative of an absolute value? So the absolute value is a function, and its convention is written out like this. So it has two bars, and there's a variable on the inside. So regardless of whether x is positive or negative, it will always pop out a positive number. So always pop out a positive x, okay? So that's what an absolute value is. And the question is asking us to derive an absolute value, so in terms of x. So let's say that y equals this. So they want us to derive dy over dx of this, okay? What is that equal to, okay? So, whoops. This is very tricky because we're never really taught how to derive absolute values and like any tricks or any kind of techniques, right? So we'll have to, I guess, redefine what an absolute value is, and we'll have to go from there, okay? So the absolute value can be thought of equivalent to the square roots of a number that is squared, right? But then this is also squared, all right? So the absolute value can be equivalent to a squared number that is square rooted and then squared again, okay? So regardless of whether it's negative or positive, the square will make it positive, and it would be square rooted and it would be squared. So the square here is to get rid of the square within, and then the square root is then undone by the square outside, okay? Oh, sorry, there shouldn't be a square here. What am I saying? Sorry about that. I got confused. Instead, so the square is to remove the negative value, and the square root is to undo the square, okay? So another way to write it is x squared 1 over 2. Yeah, I saw the junior tutor here. They wrote a square root and they put a 2 as an index, which I guess makes sense, but that confused me. So when we're saying that we want to derive this, we can alternatively write it out as the derivative of x squared rooted, okay? So we're going to use this definition of an absolute value to find the derivative of an absolute value, okay? So this is just a lot of chain rule here. So we're going to do the first chain rule, which is the outside brackets. So this equals to 1 over 2 x squared negative 1 over 2. And then we're going to do the inside brackets. So here I'll just follow the junior tutor solution. So the inside brackets here is going to be 2x. So this is the full term here. So this 2 and this 2 cancel out. So we get x squared minus half times x. Okay, cool. So this can alternatively be written as this. And this is just the absolute value, right? According to our definition. So we can just replace that with absolute value. So now we have found our derivative of the absolute value, which is just x over absolute value of x, okay? So that's the derivative. of an absolute value. So the junior tutor did the same solution. They found a different way of representing the absolute value by representing it as a number that is squared and then square rooted. And then they derived that using a chain rule within a chain rule to come to our conclusion here. And then they simplified and they recognized that x squared square rooted is absolutely just the absolute value. So they just put the absolute value in instead, and this is the solution. So the solution is correct. Cool. Okay, so next question. What is the integral of 1 over x times ln x? Okay, so in question number 3, we use integration by parts. So this time we're just going to use a u substitution. We're just going to use a variable to simplify this integral to make it easier to solve, okay? So let's write out our integral first. According to this, right? So let's call variable u. And let's say variable u is equal to ln x. So that means that du over dx would equal to 1 over x, which this could alternatively be written as 1 over x times dx. Okay, so these are our two equations here. So we're going to sub u, so we're going to sub 1 and 2 into our integral. And we have written out a new integral here. So this will equal to 1 over u du. So you see here that I subbed in u for ln x, and I subbed in du for 1 over x dx. So 1 over x dx is equal to du, and we have this. And we now know that integral of 1 over u du, according to the logarithmic rule of integration, is just equal to ln of u plus c. Okay? And now we're going to sub back in our u here, which is just ln x. So sub 1 in, or sub u equals ln x in. And therefore, this equals ln of x plus c. Okay, so we use substitution as another technique to solving these integrals easier. So the junior tutor also did this, so it's correct. Okay, cool. All right, let's move to question number 8. All right, so find the maximum, and absolute minimum values of f of x on the given interval 3 plus 81x minus 3x cubed. So in question number 4, we found the local maximum and minimum values, all right? So the difference between this question and the question number 4 to question number 8 is that we're finding the absolute maximum and absolute minimum of a single variable function. And the reason why we can find the absolute maximum and absolute minimum, because we're given an interval, all right? So in multivariable functions, if we're giving an interval, there may be possibly an absolute maximum or absolute minimum within a given interval, okay? Without this interval, we might be looking at local maxes or local mins, or absolute max or absolute mins, depending on what the function is, right? But since it gave us the interval, we can now call it, instead of local, and we can call it absolute max or absolute min, okay? So the junior tutor laid out the strategy of solving these kind of questions. First of all, we need to verify if the function is continuous on interval a, b, okay? If there's any discontinuations or any jumps or any holes, this would make our solution invalid because there might be values that it might not be continuous on this interval, basically, right? So we need to make sure that it's continuous, first of all. So we need to find the critical points of f of x at a and b. So that requires us to find the derivative of our function, setting it to 0, and finding the values of x that will solve that equation, okay? So then after we find our critical points, we need to plug those critical points or those x values back into our original functions to evaluate whether or not they're maximum or minimums. We also need to test intervals here because the intervals are not going to be included in our critical point values, right? But however, they could still be absolute maxes or absolute min. So we still need to check our interval of 0 and 4, right? And after that, we can finally identify what is our absolute maximum and minimum within our graph and this interval, okay? So first of all, let's verify the first step here, okay? So the first step is to figure out whether or not this function is continuous on the interval, all right? And a quick look at the graph will show us that this function is continuous on all real numbers, okay? We see here that there's no denominator that will make equal to 0. We also see here that there's nothing that goes to infinity here, right? This is just a polynomial. So we know at all x in real numbers, in the real number set, f of x is continuous, right? You guys can check this. You guys can also graph this. It's a very excellent way of seeing if it is a continuous function by just graphing it, okay? So we need to find the critical points now. So we need to calculate f prime of x, okay? So f prime of x will be equal to 81 minus 9x squared, okay? We want to factor that, which is just x squared minus 9. Okay, so, and that's just equal to negative 9, x plus 3, x minus 3, okay? So now we need to set f prime of x to equal 0, which sets this equation to equal 0. And now we need to find our zeros, right? So our zeros here are x equals 3, negative 3, okay? So we have found our critical points. So we have found out that there's a 0 rate of change, or there's a 0 slope, or at x equals 3 and x equals negative 3, okay? So now the third step is to evaluate these critical points and intervals. So evaluate f of x at 3, negative 3, and we need to check our intervals too, so 0 and 4, okay? So f of 0 would equal to 3, okay? F of, whoops, why do I have a bracket here? F of 3 is 3 times 81 times 3 minus 81, which is 165. I'm just looking up the thing. And we're also going to evaluate f of 4, which is equal to 135. Okay? So we're just going to plug in those values. And the reason why we did not evaluate negative 3, even though it is a critical point of this function, is because it is not in the interval of 0 and 4. So we don't need to calculate it, okay? So finally, we have our 3 points, and we can now identify what is a local maximum, or absolute maximum, absolute min, okay? So this here is our absolute min. And 165, or f of 3, is our absolute max. Okay. So finally, we can write our concluding statements. So f, let's just write 0 and 3 is our absolute min of f of x, and f of 3, oh, why do I keep writing f? And 3, 165 is the absolute max of f of x. Okay? So this was the step-by-step strategy of solving these kind of questions. And you guys will really encounter a lot of these kind of questions because they're very simple, but they test a lot of core principles and theories. Okay, so the solution is correct. Good work. Okay, cool. Let's move along to question number 9. All right, so the next question is find the exact length of a curve at y equals x cubed divided by 3 plus 1 over 4x at the interval of 0 and 2. Okay, so let me just write that out here. Y equals x cubed plus over 3 plus 1 over 4x at 1 at this interval, or we can write it as, okay. So I'm not going to go into the proof of how to find the formula for calculating the length of a curve, but the formula for length of the curve as established by the junior tutor is this. So we call it arc length. And that equal is the definite integral from BA, interval AB, of the square root of 1 plus the derivative of fx squared, okay, of dx. So this is the formula for calculating the arc length, okay? It has something to do with calculating, I guess, the area under the curve, but you're calculating very small intervals of it, and that way that you can approximate the length of the curve by doing so. If you want to search up the proof, just search up proof of arc length formula, and you'll find it. Okay. So in this case, the first step that we need to do is we need to find our dy over dx. Okay. So dy over dx is 3x squared divided by 3 plus negative 1 over 4x squared. Okay, which just equals x squared, minus 1 over 4x squared. Okay, so that's our derivative, dy over dx. Okay, so now we're going to plug that into our integral. Okay, so arc length, let's just call arc length A, or let's call it L, actually. Arc length L would equal to the integral, definite integral of 2, 0 of the square roots of 1 plus x squared minus 1 over 4x squared dx. Okay, so we're going to expand this first. So this is just a lot of calculating at this point. So we're going to expand it. So this is 1 plus x to the power of 4 minus 2 over 16x power of 4 plus, no, this should be, sorry. This should be 2 over 16x to the power of 4. This should be 1, I think. Okay, maybe I'll need to really just expand all of it, okay? Alright. I'll write it all up. Okay. X squared minus 1 over 4x squared times x squared minus 1 over 4x squared. And this is just all square rooted dx, okay? So let's solve this. This is going to be huge. Okay, so this is going to be 1 plus x to the power of 4 minus, so x squared times this, so minus 2 x squared over 4x squared. plus 1 over 16 x to the power of 4, all under one big square root. This can be simplified to this 1 plus x to the power of 4 minus 1/2 plus 1 over 16 x to the power of 4. Okay, cool. So we end up with this integral after a lot of calculations. Okay. This one can be simplified, so we can write x to the power of 4 plus 1 over 16 x to the power of 4 plus half, all square rooted here, dx. Okay, cool. So yeah, that was a lot. So now we can rewrite this x to the power of 4 plus 1 over 16 x to the power of 4 plus 1 over half as this. Okay, x squared plus 1 over 4x squared squared. Okay, we can write it alternatively. This can be written as that, and it's just simply like a perfect square, I guess you can say. Okay, and because of that, we can get rid of the square roots because of the square here. So all we're left with, in fact, is integral of x squared plus 1 over 4x squared dx, right? Which equals to 1 over 3 x cubed, because we're integrating now. So 2 plus 1 equals 3. Move that exponent down over here. And this is going to be negative 1 over 4x with 2 and 0. Okay, cool. And now we can calculate this definite integral, which is just 8 over 3 minus, where's my x here? My x is here. 1 over 8 minus 1 over 3 minus 1 over 4. Okay. So we're just going to simplify these fractions here. So we get 7 over 3 minus plus 2 over 8, so plus 1 over 8. Okay, and that equals to 56 plus 3, 59 over 24. Okay, so we found our arc length after a long calculation here. So we use our arc length equation, we found our derivative, and then we subbed in everything, we simplified. Then we calculated our definite integral, and then we simplified and reduced all our fractions until we got 59 over 24. And now we know that the curve of x cubed over 3 plus 1 over 4x at the interval 0, 2 has arc length of 59 over 24, or a junior tutor wrote out the decimals, which is 2.458. Yeah, so that's just units, and that's how you calculate arc length. Okay. And again, if you want to find the proof for how to find the formula for the arc length, just search it up online, and they'll go through step by step the theory and the thinking behind how to find the formula for arc length. Okay. Okay. Finally, let's move on to the last question of the day. Question number 10. How do you evaluate the limit of 1 minus cos x divided by x as x approaches 0? Okay, so if we were to calculate this limit, by normally, okay? So as x approaches 0 of 1 minus cos x of x, we got 0 over 0, which is indeterminate, okay? So there is a method of calculating these limits when you have indeterminate form. So another indeterminate form is, I guess, like, so let me just write off indeterminate forms, okay? So we have 0 over 0, we have infinity over infinity, we have 0 to the power of infinity, and so on, okay? So if you guys want to look for the full catalog of all the indeterminate forms, these are basically, we cannot calculate it any further because we don't know what 0 divided by 0 is, or we don't know what infinity is divided by infinity is, okay? So the Hopital's rule is can be used to calculate these kinds of limits. And the only criteria for the Hopital's rules, so the Hopital states that the limit as x approaches a of a quotient of functions is equal to the limit as x approaches a of their respective derivatives, okay? As long as the limit of x approaches a of f prime of x and g prime of x exists, okay? So it has to be a value, all right? So as long as the limit exists, then L'Hopital's rule can be applied, okay? So we're going to solve our question here now. We're going to use L'Hopital's rule. Okay, so we have the limit. That's way too thick. So we have the limit of 1 minus cos of x divided by x as x approaches 0. So if we derive the top, so let's say d of dx of 1 minus cos x. So we know that the derivative of cosine is equal to negative sine, but since it's negative cos, we're going to have sine x. And the d of dx of x is 1. Okay, so now we want to calculate the limit of x approaches 0 of sine x and 1. Okay, which is just equal to limit as x approaches 0 of sine x, and sine of 0 is just 0. So now we have found our limit of this actual function by using L'Hopital's rule. So the limit of 1 minus cos x divided by x as x approaches 0 is 0 using L'Hopital's rule. Okay, so this solution is correct. Okay, so so we realized that 1 minus cos x over x as x approaches 0 is indeterminate. So we use L'Hopital's rule to calculate the limit. So we derived both the top function and the bottom function. So the top function is 1 minus cos x. 1 is a constant, so that's equal to 0 when we derive it. And negative cos x, the derivative of that is just sine x. Okay, so that's the derivative of the top. And the derivative of the bottom is just x. So the derivative of x in terms of x is just 1. So then we just get the limit of sine x as x approaches 0, and sine of 0 is 0. Okay, so we have found our limit of our original function by using L'Hopital's rule. And L'Hopital's rule is very useful in these kind of settings when you cannot calculate the limit using normal conventions like substitution or algebraic methods, or using the conjugate or whatever. Okay, cool. So that wraps up our session for today. I hope that you guys learned something, and if any other questions regarding your calculus homework or any kind of questions on the test that you guys were struggling on, please submit them through OneClass, and we'll try to get to them as soon as possible. Thank you so much for listening, and I hope you guys have a good night.